Good day, everyone. My name is Branko Savija, and I work at Delft University of Technology. My today's talk will focus on the role of models in understanding, developing, and design of cementitious materials. This is an overview of my talk. I will first give you an introduction to the topic, then focus on different aspects of understanding, developing, design of materials using models, and finally draw some conclusions based on what has been presented. In introduction, I would like to give two propositions on why we need models in materials and civil engineering in general, and how we should use these models. Proposition 1 says that the purpose of computing is insight, not numbers. What I would like to draw from this is that actually we should not develop our models in such a way that we get a perfect match between our simulation results and experiments in terms of numbers. Rather, we should use models to understand our experiments better. In experiments, it's often difficult to isolate certain parameters and to control them. In simulations, it's normally very easy. And this is what is nice about using simulations for understanding of the material behavior. Proposition 2 says that both theory and experiment play their role in the progress of science and engineering, and the interaction is crucial. Those doing the experiments and those involved in theory development must speak the same language. What I mean by this is that often we have sometimes two different fields of experimentalists and theoreticians or modelers. And sometimes it's very difficult to have them working together. Preferably, the same people should be doing both experiments or simulations because the synergy of the two will help us understand our materials the best. So this synergy between experiments, advanced experiments sometimes, and mostly numerical simulations can help us create new materials and ultimately better and safer structures. Of course, we should not forget experience, using empirical parameters and safety factors that we have learned in the past 100 or so years in civil engineering. So here I would like to introduce a class of models that we use quite extensively at Delft and that will be discussed in a bit more detail in this presentation, which is a class of lattice models. These models have been introduced in the 1940s by Hromnikov, who suggested to discretize a continuum with the lattice or truss elements. If you make these trusses infinitesimally small, we will obtain an exact solution for the deformation of the body. And the first truss proposed by Hromnikov had a limit of a Poisson's ratio of 1/3. Based on this definition, you would already see what the problem was in the 1940s. You would need to have very small elements, and this was not possible until computation power increased significantly. So the models were not very much in use until around 1990, where people from theoretical physics adopted them to study a fracture of disordered media. So this was very nice for people working with concrete because concrete is a disordered medium. So what is the principle of the lattice model used, and especially more specifically the one that we use at TU Delft? The general procedure that we use is as follows. First, we discretize the continuum as a network of beams or spring elements. Then we implement disorder in a certain way that we'll discuss a bit later. Then we apply external load or deformation. We assume that each element has an ideally brittle behavior, so that has a linear relation between the stress and the strain, and it works in a brittle way. We then perform a linear elastic analysis of the whole system. We calculate stresses in all beams, and then we identify a beam that has a maximum stress to strength ratio. This beam is then removed from the mesh, thereby creating a small crack. And after that, we relax displacements and repeat the whole procedure once again. Remove the following beam. This way, we can simulate crack growth in our cementitious material. In 2D, here is how it is related. So we relate the forces at the beam ends to the stiffness matrix to displacement of beam ends. And for simple triangular lattice, we can also analytically relate the parameters with the bulk modulus, the shear modulus, and the Poisson's ratio. However, concrete is a heterogeneous material, and heterogeneity can be implemented in lattice models in different ways. For example, we can generate the particle structure of our material using a Fuller distribution, and then use this as a basis of formulating our lattice. How do we do that? We simply overlay our lattice on top of a material structure and assign different properties to different beams. If both beam ends are within an aggregate particle, we assign it the material properties of an aggregate. If both beams are within the matrix, we assign them with the matrix properties. And the mixed beams have properties of the bond. And this way we can assign different mechanical properties to different parts of our model. How do we use models to understand the behavior of cementitious materials? We frequently talk about concrete as a multi-scale material. According to Whitman, concrete can be seen as a 3-scale material. Microscale, where we can distinguish different hydrates embedded in the cement paste together with capillary porosity and unhydrated particles. Of course, we can also go lower to the nanoscale, but we will not do that in this presentation. The mesoscale, which is a scale roughly of mortar, where we can distinguish between aggregate particles embedded in the cementitious matrix, and concrete scale, or a continuum scale, where we assume that concrete is isotropic and homogeneous material. And this is actually at the concrete scale where we do most of our testing. We test our compressive strength, our flexural strength, assuming that concrete has certain homogeneous properties at this scale. We can also do similar tests in a bit more difficult way at the mortar scale. So we make smaller specimens where we can still test compressive strength, tensile strength, and similar properties at the mortar scale. But what do we do at the cement hydrate scale? How do we determine properties of these individual phases at the cement hydrate scale? Well, classically in the past 20 or so years, people have been using nanoindentation, statistical nanoindentation, for example, to determine the properties of different phases in hardened cement paste. What we get from nanoindentation is the elastic moduli of different phases, but we don't get the strength properties. On the other hand, at Delft, a colleague of mine has developed a multi-scale modeling framework already some years ago, whereby we would be able to go from the microscale all the way to the macro scale by passing properties calculated at lower scales. However, for this, we need to have reliable estimates of properties of different hydration phases at very small scale, which is generally not available. So in Delft, we developed a technique for creating very small specimens, a so-called microdicing technique. We make a thin specimen, sort of a thin section of 100 micrometer thickness, that we dice in 2 directions, and then create an array of microbeams. These beams can then be tested. So this is how they look like under an electron microscope. And we test them using a nanoindenter. And we can load them, we can measure the load and displacement, and measure the total force needed to break these specimens. So under a Berkovich indenter, this is our fracture process of this small microcube looks like. And we get a load displacement curves for these beams. Well, displacement in this regime is actually where the indenter sort of catastrophically breaks the specimen, but the first part gives us the stiffness and the strength of these microcubes. However, this still doesn't give us properties of individual phases. So here we use numerical models to do inverse analysis and estimate the properties of different phases. So we created models with different water cement ratios, and we simulated them using the same loading and boundary conditions as given in the experiment. And with that, we could estimate the strength of different phases in our cementitious matrix. The stiffness we already knew from nanoindentation, so we had only one unknown. And assuming that the ratio between the strength and the stiffness is constant for different phases, we were able to estimate properties of different phases in the cementitious matrix. However, apart from the matrix, we also have an ITZ in our cementitious matrix. So using a similar technique, we created microcantilevers that contain part of an aggregate in the bottom and part of the cement paste in the top. And then these microbeam specimens were loaded in flexure. And with that, we could calculate or measure first the strength of the interfacial transition zone. We can also observe the fracture surface, which also has some debris from the hydration products that have precipitated onto the cement paste. onto the aggregate particle. We could then use our lattice model to simulate the same process, and from that, calculate back the properties of these contact elements between our lattice mesh of the paste and our aggregates. And this gives us all the properties needed to simulate mortar on the following scale. So we calculated properties of hydrated cement phases, and from that we can estimate the properties of the cement paste. We have the properties of the ITZ, and gives us the basis to simulate mechanical properties of mortar on the following scale. So we performed experiments in very small mortar specimens of 10 by 10 by 10 millimeters with a notch and with a controlled grain size, so we can easily discretize it using our model. And we simulate the same experiments with embedded mortar particles instead of a cementitious matrix. And we also, with computed tomography, we could also get the air voids and put them in our model. As I said, from the smaller scale, we have the properties here shown in black of the cement paste, which we then discretize in a multilinear way and assign to the cement paste elements, which are here in gray. And we do the same for the ITZ elements. We also have calculation results from the smaller scale. We discretize these results and put them into the interfaces. And we have an excellent match between the experiments shown here in gray and the modeling results shown here for different cases. I will not go into detail, but we tested different scenarios. We have an excellent match between the modeling and the experiments. And also in terms of crack path, this is how a crack looks like in the experiment, where we have a tortuous crack path coming from the notch. And the same thing in our experiments, where we have cracks going around the aggregates, of course, because the interfaces are the weakest links, but also getting a tortuous crack similar to the experiments. What is important to notice that in this case, we started from the micro scale. So we measured only at the micro scale, and on upscaling, we didn't do any calibration, any fitting, or adding any empirical parameters to get a better match between the experiments and the simulations. So this presents experimental and numerical framework on for multi-scale modeling of mechanical properties of cementitious materials that can be easily repeated for different properties, for different matrices, with different additives, for example, such as nanoparticles, and so on. We have then expanded this framework to simulate also time-dependent phenomena in cementitious materials. A first example that I will show here is the creep. As we know, cement paste is sort of a viscoelastic material that has increasing deformation with constant load over time. And then we use the same framework, same experiment. So we have cementitious matrix specimens cut here in a form of cantilevers. Then we load them using a nanoindenter. What we also did was that we created small specimens that were scanned using an X-ray CT. And then from there, we can easily segment different phases within the cementitious matrix and use that as input for our simulation. So for different water cement ratios with segmentation procedures, we could generate inputs for our numerical model of creep. So we have experiments of creep, we developed a numerical model of creep, and we simply repeat the same thing. So we have here a cantilever loaded in the tip, same thing as we do in experiments. And I will not go into detail how this was done, but in this publication, you see how we can get an excellent match between calculated and measured specific creep compliance in different water cement ratio pastes. So the experimental and modeling framework has been expanded also to include creep. Another phenomenon that we looked at is the fatigue, the phenomenon of increasing damage with repeating loading in the cementitious matrix. So we repeated the same procedure where we have scanned micro cantilever beams. We also tested them using the same approach as shown before. And for different water cement ratios, we generated different microstructures for the model. In this case, we needed to have a bit more complex constitutive law where we needed to include also increasing damage in the matrix with load repetition and also unloading damages. But with this approach, we're also able to simulate the fatigue compliance for different water cement ratios in our micro cantilevers. And also what we have seen is that actually in the level of cement paste, the damage is very minor. So very little change in the elastic modulus in very, very long time, in a lot of cycles. And then there is sudden loss of elastic modulus and sudden damage. So this is something that we found was also very interesting experimentally, but we were also able to numerically explain how and why this happens. So these models that I show here were physical models. Furthermore, they were experimentally informed. So every model had experimental input and experimental validation. But in this day and age, maybe we can skip the physical modeling altogether and try to understand the behavior of our materials purely from data. So we have been working also on data-driven approaches using machine learning to understand behaviors of our materials. So we have performed some calculations and developed some models that are able to relate the mix design and compressive strength of concrete materials. There is a widely available data set that we use to train and validate our machine learning models, different machine learning models. And we showed that different models can be used with different success to relate the mix design and the compressive strength. What we also observed, which people usually don't report, is that if you change the data set and you try to use your model on data that it hasn't been trained on with a different distribution, the model doesn't really work. So it is important to use the same distribution of data to train the model and to validate it later on. If you don't do that, the model will not be successful. We also developed ensemble machine learning models to relate the mix design and different exposure conditions, time of loading, temperature, age, relative humidity, and so on, to the creep response. And what is interesting about this approach is that we can not only relate the input parameters to the output, but we can also use the models to see how much impact each of the input parameters has on the output. For example, here we see that time of loading has a very large positive influence on the creep. So let's say the earlier we load, we have the higher creep. And we can do that. And this type of models can help us understand actually sometimes things we cannot experimentally observe. In terms of creep, it was very nice that we could do this because we could see that the model also corresponds to our understanding of the process. But there, in more complicated processes, we might be able to reveal some mechanisms that we don't really see ourselves. Another approach that we recently attempted was to predict properties of materials for microstructural images. So we have performed X-ray CT of cement paste, and we, based on X-ray CT data, we created a convolutional neural network, which is able to predict the creep modulus only from the microstructure. Of course, for this, we used the model that I presented before for creep calculations. So we trained our network based on the modeling results, and then we tested whether we can then use this trained network to predict the creep modulus, and this worked very well. So you can see more details in this recent publication. So this was about understanding of cementitious materials. We can also use models to develop cementitious materials, and I will show a few examples in the coming slides. In Delft, we have been working quite extensively with self-healing of concretes in different ways. What we see is that usually this process is very empirical, where we understand how things work, but then we need to do a lot of experiments to get good behavior and to optimize the material. We have recently also developed a numerical model within the Lattice modeling framework that can help us design self-healing concretes with superabsorbent polymers. So again, here we can also see what happens in experiments, that we have swelling of SAP particles under exposure of water and formation of macropores if that happens at an early stage. So this SAP particle needs to swell in order to block the transport of water, possibly containing harmful species inside of the cementitious matrix. We can also simulate that. We pack SAP particles inside of a box, and then we simulate the cracking process. After that, we can simulate the healing process and the penetration of moisture. So for different percentages of SAPs ranging from 0.5% to 1.5%, we see that our model is able to predict that less and less water saturation around the crack happens if we increase the SAP percentage, which is what we expect. Furthermore, we can also examine how a crack width influences the sealing of this concrete with SAP. So we see that as we increase the crack width, we have more water penetration around the crack, even with the same amount of SAP. So there is a balance between how much SAP you need to put and how big cracks you can heal. And also in this publication, we provide nomograms so we can relate and design these materials for different input parameters in terms of SAP percentage, in terms of the swelling capacity, and in terms of the anticipated crack width. We have also been working on 3D printing of concrete. Of course, a lot of people are working on that. So you have an extrusion-based process where you extrude layers of material on top of previous layers and try to build up a structure. However, as you see in this video, if the parameters are not done correctly, the structure will collapse. So what we need to be able to predict at which point, will the structure collapse in the fresh state in order to optimize the printing process. So you see already some structures have been built using this technique. So it's not only a lab-based technique, there's really a lot of interest from the academia, but also from the industry in this. So if you look at 3D printing of concrete, there are two basic failure modes. Plastic collapse, where usually a bottom layer of the printing structure cannot sustain the weight of the layers on top of it, and then the structure collapses. And elastic buckling, where there is a loss of stability inside of the print during the printing process, either due to imperfections or due to geometry. So actually, we should be able to simulate both of these failure mechanisms if we are to predict the buildability of cementitious materials and if we are going to control the printing process. So a PhD student of ours has developed a numerical model in the Lattice modeling framework that is able to simulate the failure modes of plastic collapse. So we can predict at which point the structure will fail during printing based on the input parameters that are experimentally measured. So we then can, the model has been validated against experimental data from the literature. So based on the geometry and on the material properties, we are able to predict at which point will the model or the print fail during 3D printing. The second failure mode is that of elastic buckling, and that commonly happens in, for example, wall structures. And on the left-hand side, we see a simulation of the process. And on the right-hand side, we see an experiment. And we can see that at this stage, we are able to simulate qualitatively the mechanism and the process, but we're still trying to fine-tune the model to get a better match in terms of quantity, in terms of how many layers can be sustained before the material fails in elastic buckling. So this is something that is very important if we are to optimize the printing processes in practice. And finally, looking at the design of construction materials and how we can use numerical models for design of these materials. We have performed some studies on use of 3D printed reinforcement in cementitious materials. So with 3D printing, we have enormous freedom of how we can design and fabricate the reinforcement. So basically, we use a 3D printer, and we can fabricate the reinforcement of any shape or form that we want, of course, within the limits of the printer that we have. But in principle, it offers much more freedom compared to traditional building processes. So what we did, we designed several very simple meshes in triangular shapes. So we have what we call large triangles, mixed triangles, small triangles. And with 3D printing, you can also influence the roughness of the mesh. So you can build in edges similar to ribbed bar reinforcement to increase the bonding between the reinforcement and the matrix. And then we cast these into mortar bars and tested them in 4-point bending, in flexure, and in uniaxial tension. And because the presentation is about the use of models, we have also created modeling representations within the Lattice modeling framework of all these three different experiments. So first, experimentally, we saw that with large triangles, we cannot really get multiple cracking and deflection hardening. But in 4-point bending, we can do that with mixed triangles. So we have an increased reinforcement density in the middle, sort of a functionally graded material, and with a small triangle. So if we increase the percentage of 3D printed reinforcement, we can get, of course, better behavior. And our simulations show that. So this is for the large triangles. For the mixed triangles, we have multiple cracks inside of the bending span, and for the small triangles as well. And in uniaxial tension, we see that this is our reference material, which is of course very brittle. With large triangles, we can have a few cracks, but they're mostly obtained by pull-out of the reinforcement. And if we go to small triangles and small triangles with ribs, we can get multiple cracking and actually very nice strain hardening behavior, similar to what you get, for example, in ECC materials. So then we wanted to bring this concept further to functionally grading materials. So we designed an octagonal reinforcement that is denser in the middle than on the outside. And we embedded these reinforcements inside of the cementitious matrix. So what is important to keep in mind, and we sometimes forget, is that 3D printing process that we use and that most people use is FDM. And in that process, there's also a print orientation. So depending on how you print, the material properties will be different. So we keep that in mind when we print, but also in our numerical simulations. So we created also a simulation of this 4-point bending experiment. We use symmetry to cut down on the computational load. And we use, in this case, Abacus with a CDPM model to simulate the process of deformation and fracture in this material. We can also then vary the properties of the material. So we can say, okay, what happens if we change the reinforcement we can print and print a stiffer one or a stronger one? And what we show is that actually, if you adjust these properties, the properties of the reinforcement, the stiffness and the strength, you can also get multiple cracking inside of these materials. So we showed that in terms of models. We were not able to achieve that in terms of experiments, but what we know now is we know in which direction we need to develop our design in order to get certain properties. So in this way, the models inform the experiments. We have also done some work in development of Auxetic cementitious composites. So what does this word Auxetic mean? Conventional materials have a positive Poisson's ratio. When we compress them, they laterally expand. Auxetic materials are the opposite. When we compress them, they contract. So they have a negative Poisson's ratio. And in certain applications, these properties are very, very useful. So we try to see whether we can create materials that have these properties using a cementitious matrix. So here I will show you a video what we achieved. So we created a certain pattern, and with a fiber reinforced material, we were actually able to achieve material that contracts laterally upon compression, so has auxetic properties. However, the mechanism of auxeticity in cementitious materials is different than that of polymer materials that are, or rubber-like materials that are commonly used in the literature. So we used, again here, CDPM, first to simulate the deformation and fracture process of the material, but more importantly, we used the model to understand why and how we can achieve this auxeticity. So the model, what the model told us is that with elliptical shapes of these holes, we have stress concentrations at the tips of the ellipse. These stress concentrations cause microcracks that are then bridged by the fibers present in the matrix. And then they rotate. If we didn't use the fibers, the specimens would simply explode, which we also observed in some trials in the lab. So it is the fibers and the shape of the ellipses that allow this quasi-plastic behavior of these joints, and also the rotation that enables auxetic behavior of these materials. So this is very nice that we can use models to explain behavior from the experiments. So finally, this leads me to some conclusions. First, realistic models can be used to complement and understand experimental observations. We do not always have all the details in terms of the experiments that we perform. And if we have a model, sometimes we can see things that we don't observe that easily experimentally. And then we can understand better how our experiments work and how our materials work. Second, Models that are validated can provide guidance to physical experiments and can reduce experimental efforts. So we have a good model, we can use it to design experiments and therefore reduce our trial and error approaches. And we have seen that in this presentation and in our work in terms of, for example, self-healing materials. Models can discover new materials. I didn't go that much in detail, but what we saw in terms of the Auxetic material is that if we can explain the behavior, we can use the models to fine-tune the behavior of these materials. So optimization and material discovery in principle is possible using numerical models. And finally, I would like to conclude that perhaps we as a community, we should start looking into data-driven models, not only in terms of, simple regression models, but also models for material development. And maybe these models represent the future in terms of the development of cementitious materials. And with that, I would like to finish my presentation and thank you very much for your kind attention. And I will be available for questions. Thank you.